St. Michael's College, speaking about multivariable Tutte functions and transition polynomials.
Beauty. Like many of us, so thank you to the Newton Institute, and I also need to acknowledge the NIH and the NSF who've been funding my work for the past several years. Just to establish the terminology here, to make sure we're all speaking the same language, I'm going to call this thing here the self loop. This is a loop. These guys have already been called other things here, co-loops, co-cycles. I'm going to call them bridges. You'll hear them called co-loops, isthmuses, cut edges. I'm sure I'll learn a couple more terms for them. I'm going to call them a bridge. Okay? And it's just a single edge whose deletion creates more components in the graph than you had to begin with. We've already talked about deletion and contraction, but the one thing, so deletion is just to take an edge out, contraction is just to make it smaller and smaller until the two endpoints are identified and the edge is gone. The one thing I did want to just touch here is I'm going to call, oops, where'd my pen go? I'm going to call something like this a cycle. Okay, so what was it called before? Non-self-visiting loop. Okay, whatever. I think we were calling these polygons before too. So I'm going to call something like this a cycle, and something like this that's allowed to come back and visit any one of its vertices before it returns to the starting point, I'll call that a circuit. Okay. So here's the story. I'm going to start with sort of the classical Tutte polynomial or Potts model partition function, some multivariable versions, and then sort of the fullest possible multivariable extension of that given commutativity. Then I'm going to tell the same story, exactly the same story, for a different kind of graph polynomial. Okay, one that's computed on vertex states instead of edge states. But exactly the same story. There'll be a classical version, some intermediary multivariabilization, and then further multivariabilization. These two kinds of polynomials are related to one another on planar graphs via medial graph construction, and this lets the two kinds of polynomials inform each other. Then, for the second kind of polynomial, since we know a lot about sort of some of the theoretical tools that are available for the Tutte polynomial, I'll concentrate a little more on the second kind of polynomial. The second polynomial is a Hopf algebra map, and that will give us structural theorems for extracting information from that polynomial. Okay, so that was the talk. Anybody who wants to go to sleep now or work on some other really pressing problem, you've got it all.
We'll only
okay.
Go to sleep when you start talking about
Hopf algebras. No. Okay, no, this is really, really important. There are some further Hopf algebra talks coming, and nobody's really talked about them. And they've said the word. And I always have this philosophy that at a conference, I'm never the first one to say the word Hopf algebra, but if somebody else has said it, I figure it's fair game. And I not only heard the Hopf algebra, but I heard Mobius function. So I'm all excited now. But there are some later Hopf algebra talks, so I do have a little bit of a very elementary introduction that maybe will help support some of those later talks and let them do more exciting things without having to do basics. Yeah, so I'm going to go over the Tutte stuff a little bit quickly because we've had some lovely exposition on it already. But there's the classical dichromatic polynomial, so Whitney and Tutte back in the 50s. Potts model partition function, if you do, I don't want this to die on me here. If you do these substitutions, Andres showed us last time how you can recover this form of the classical dichromatic polynomial by writing this as a product and doing these summations. All right, but what I want to draw attention to here is that in these very first models, the edges had a constant interaction energy. So we didn't have freedom in those edges. The essential properties for this dichromatic polynomial, and again, we've seen some of this already. You have a deletion, contraction, reduction relation if the edge E is not a loop. You have a multiplicative relation on disjoint unions. And a final, these two together will reduce you down to, I can't remember what I called them blossom graphs, somebody called them something else today, but a single vertex with a bunch of loops off it. And this then tells you how to evaluate that terminal state. These properties capture the sort of essential local physical properties in the Potts model, in that if you have two spins with different energies, two vertices with different spins, there's no interaction, so there might as well not be an edge between them. If you have two vertices with the same spin, they interact with their neighbors identically, so they might as well be coalesced into a single vertex with perhaps some weighting. So that's what I mean when I say it captures the essential local properties of the Potts model. And these are defining theoretical tools in that you can define the dichromatic polynomial via these instead as we saw it before. Okay, some of the kind of first multivariabilizations. This was a much more natural idea, I think, in physics to have variable energy edges, so it's not surprising that this showed up first and showed up a little bit later in the math literature. But these two models have a deletion contraction with an edge weight on just on the contraction piece. The Fortuyn and Castellan model looks doubly weighted. It has a weight for both contraction and deletion, but they're probability models, so the sum of those two are 1. So you really only had 1 degree of freedom here.
What is really important for this equation?
The breakdown of the proof in here, the integration breakdown actually uses it, and it's assumed in the model. He does the integrals to prove this reduction.
Integrals, you mean sums? Or?
No, literally integrals, the probability integrals. Yeah. And uses this. I don't think it's necessary, but it's just it was sort of part of the underlying assumption that was there, that these would always add up to 1. What is that? Anyway, I'm not doing it. I'm going to take a little shift here. The classical Tutte polynomial is a translation of that dichromatic. Properties are a little bit different. The deletion contraction holds only for ordinary edges that are neither bridges nor loops. And that lets you reduce the graph down until you've only got bridges and loops left. In other words, you're left with forests that have loops on them, and you can evaluate that as x to the number of bridges and y to the number of loops. This can be how do I want to say this? this last condition can be achieved equivalently by pulling out bridges with a factor of x, pulling out loops with a factor of y, and specifying that the top polynomial on a graph with no edges and n vertices, that's what I mean by the E sub n, is just 1. All right, but if you think about this, you kind of got 5 pieces that it would be nice to be able to play with. All right? You've got the E sub n. Maybe you don't want that always to be 1. Maybe some reason you want to keep track of the vertices. You've got what goes on when an edge is removed as a loop, what goes on when an edge is removed as a bridge, and sort of 2 things going on if his edge is removed as an ordinary edge in the computation tree. And it would be sort of lovely if you could make those all independent variables. You never really get what you want, though, because we're constrained here. You want to make sure that you get a well-defined function that preserves those properties of deletion, contraction, reduction, and some kind of multiplicativity. And you get constrained. So what I mean by the order of operations, if you delete and contract on this edge and you delete and contract on this edge, if you do things in a different order, you get very different sets of graphs. And there's no reason to expect that the final answer that you get will be the same if you let all those variables be just free. In fact, it's kind of remarkable that you get it at all. And what happens is that whether or not your function is well defined boils down to whether or not it's well defined on these 3 very small graphs. And these 3 very small graphs give 3 equations that must be satisfied in order for the fully multivariate version to be well defined. And where these come from simply come from putting a label of lambda on this edge, a label of mu on this edge, parameters, big X sub lambda, big Y sub lambda, little x sub lambda, little y sub lambda on this edge, and doing the deletion contraction in both ways and saying, those have to be the same. So that's all that's going on there. Necessary is real clear. What's remarkable is that this is sufficient. If you're good on these 3 small guys, you're good everywhere. Now, doing this in sort of full generality over arbitrary rings that don't even necessarily have unit introduces options for a lot of really annoying pathologies, which sort of indicate that you're really up against the edge of how far you can push the theory. So I'm not going to go there because it's a very ugly place. But I do want just to pass that out, that if you're not in a nice field, if your class of graphs isn't like all the graphs or all planar graphs, there are some places where you can get tripped up. So to be a little careful with the theory. If you're in nice places, you do get something, and in fact, you need to sort of be in nice places to get something analogous to the dichromatic polynomial. And in reasonable situations, if these parameters are taken in a field, you're allowed to divide. Dividing is just good. You're constrained on your loop values, but this constraint means that those 3 equations are immediately satisfied. And you get something that looks exactly like a dichromatic polynomial But here you do get 2 degrees of freedom in the weights. This here, let me also give a little bit of a warning here. You can do some factoring out to rewrite like this. You do need to be careful of the prefactors. The prefactors in this theory, just like the difference between the Tutte and the dichromatic polynomial, the prefactors affect the algebraic properties. They affect the multiplicative properties. So if it's important to maintain multiplicative properties, you've got to be careful what you do with your prefactors. For example, the dichromatic is multiplicative on disjoint unions but not on blocks, whereas the Tutte formula, classical Tutte formulation is multiplicative both on disjoint unions and on blocks, which is why it's typically the form that's used for matroids. So that's the caveat about the prefactors. All right, so that was the Tutte story. Going to go tell the same story again for Martin or circuit partition polynomials. These were developed by Martin in his 77 thesis, and there was one paper. I get this feeling it's going to be a little bit like Ising. That's it, no more. I think he was a graduate student of Jaget. The theory was then subsequently developed by Las Vernas and then built on later. But you start with an Eulerian graph. I'm being a little loose with the term here. I don't care whether or not the graph is connected. I just want all the vertices to have even degree. Or an Eulerian digraph, which means that the edges are directed, but at every vertex, the number of in degrees is equal to the number of out degrees. And then this is the circuit partition polynomial in the unoriented case. This is in the oriented case. These are just generating functions for the Eulerian K partitions in a graph. All right, so what's an Eulerian K partition? A 1 partition's just an Euler circuit. A 2 partition are 2 circuits that are edge disjoint and cover the graph. A 3 partition are 3 circuits, again, edge disjoint and cover the graph. F sub k of g is just the number of k partitions. So that's all it is. It's a generating function counting the number of k partitions in an Eulerian graph. Exactly the same game in the oriented case, except that your circuits have to be consistently oriented.
Conversely, you are not introducing the polynomial for counting orientations of a given unoriented graph. Is it?
No, I am not. That problem is hard. Yes. There's a, was I talking about that? Anybody? Yeah, there's a paper by Peter Winkler, and who's the other guy? I forgot. Do you remember? Yeah, sorry. That's an NP-hard problem. So yeah, I could write down a generating function for it, but I wouldn't be able to do much. These also have state model formulations. You can look at a vertex and think of the possible states at a vertex as being the possible ways of pairing the edges. Okay? So in the unoriented case, you've got 3 possible vertex states. If you choose a state at each vertex, you get a state of the graph, which is exactly equivalent to a K partition, where K is just the number of components that you get in the graph state. And so you can sum over all of the graphs, x to the number of components, or equivalently, you have a recursive, a linear recursion relation. You can just do this one vertex at a time, analogously to the deletion contraction in the Tutte polynomial. All right, so these give you theoretical tools that are valuable in graph polynomials. It's very nice to have different ways of computing the graph polynomial to set up the equivalences and here for induction arguments.
Could you say
again, what is the thing analogous to deletion contraction?
The thing analogous to deletion contraction is that you have a linear recursion relation that lets you break down a big graph sort of one point at a time.
Or so you look at the three possible
Yes.
states at one vertex.
Yep. And so the polynomial, the circuit partition polynomial of a graph with a vertex v that looks like this is the sum of the circuit partition polynomial where that vertex has been replaced by this state, where it's been replaced by this state, and where it's been replaced by this state, with coefficients, in this case, of 1. Okay, because this is the classical model.
It has degree 4, or you want to introduce it for arbitrary degree and make longer strings?
This is the classical case, but that's exactly where it went. I mean, that's the obvious thing to do. Martin's original work only did degree 4, just like in the Tutte case, in the original case, all the interaction energies were the same. Did I tell you this was going to be exactly the same story twice? It really is. Just exactly parallel development. But yes, this is the next sort of obvious generalization here. Although it didn't go that direction first. Well, sort of. Las Vernas did generalize it to arbitrary Eulerian graphs, but didn't put weights on them. Okay. So Jaget took the next sort of multivariabilization step of, instead of having these weights all be 1 or 0, let these weights be whatever we want them to be. Okay, and it's always sort of nice to have little examples. So we'll have a little example. If I assign a weight system to a vertex that assigns a value of 1 to non-crossing states and a value of 0 to a crossing state, if I take this graph and split at this vertex, first this way with a coefficient of 1, then this way with a coefficient of 1, then the other way with a coefficient of 0, you get these two. And then you do it again at this vertex, you get this one and this one for the two ways of splitting it, this one and this one for the two ways of splitting it, and then you just count components, an x cubed, 2x squared, and an x. So that's how this works. All right. To fully generalize this, now I have to hesitate here. This is not a full, absolutely pushing the boundaries of how far this can go generalization as the Tutte polynomial. The theory just started later, it hasn't gotten that far. There are actually 2 multivariable generalizations. I literally flipped a coin. I didn't know which one to talk about, but I will say there is another one. This one has the multivariabilization on the states, but doesn't keep track of kind of the lengths of the components. The other one is defined for all graphs, not only Eulerian graphs, and it tracks, the multivariable tracks the lengths of the cycles and the lengths of the paths. And presumably these two theories can be put together, but it just hasn't happened yet. So here, again, your degree on your vertex can be whatever as long as it's even. And you have pair weights assigned to every pair of edges. So this pair of edges has a weight of c. This pair of half edges, I should say, pair of half edges has weight b, etc. And you do splittings in all possible ways, and you put the multivariables out in front.
But you don't, I mean, I would have thought that the most natural thing would be to assign independent weights for each of the 2D minus 1 double factorial pairings at a vertex of degree d, whereas your weights are all products.
Yes, and here's the reason why. I want this, you're going to see later on, I want this to be a hereditary family. I want to be able to split up into subgraphs. And when I split up into subgraphs, only some of the half edges are going to go into the subgraphs, and I need to know which weights go with the subgraph. That's the reason. But yes, it's very natural to do that, except I need some kind of tools to get information out of this, and it was the Hopf algebra that got me to do it. And in order to do that, I need to be able to separate the pieces out.
But does this then even include the previous one for degree 4?
Yes.
Because we have 3.
Yes.
Yeah.
Allows for
I'll show you. I'll show you exactly how. You do a little finessing with square roots. Nothing deep. But again, an example would be that I assign a pair weight of B if a pair bounds the same black edge, a pair weight of W if it bounds the same white edge, a pair weight of C otherwise, and you go through the same breakdown. If I split at this vertex, you get a pair weight of B from here, pair weight of B from here. The next split splits this way, pair weight of W, pair weight of W, and so on, and you get some big, long, multivariable polynomial at the end. Okay, I promised you that there was a connection with the Tutte polynomial. The connections are between the original circuit partition polynomial, the classical Tutte polynomial. This was done in Martin's thesis, of which I have a tape-bound, falling apart copy. Possibly the only one in existence now. And it's a construction that works for planar graphs via medial graph construction, and I'll show that to you. And it carries over directly to the multivariable case. And it's kind of pretty. I like this. Just to remind you real quick what a medial graph is. If I have a planar graph G, all I do is hang a little vertex of degree 4 on each of its edges, and those become the vertices of the medial graph. And I draw an edge right along the face boundaries, like this, right along the face boundaries like this. This is fun. Okay? And that gives me the medial graph. I face to color it by making the faces that had vertices in them black. And then I orient the edges by going counterclockwise around the black faces. Okay? And then the lovely observation that makes the relationship work is that if you look at an edge in the underlying planar graph, and here's the medial graph kind of around it, if I delete that edge, it corresponds to a black face transition. And if I contract that edge, it corresponds to a white face transition. So the two deletion contraction and the vertex splitting reduction relations for the Tutte polynomial and the oriented Martin polynomial exactly line up, and the induction immediately gives you the relationship. And with this orientation, the circuit partition polynomial is, a little decoration times the Tutte polynomial. We good?
Vice versa, if you were having at the beginning the other polynomial, but with weights for the crossing, you couldn't go back.
Right. Right. The transition polynomial encodes a lot of information that's very different from the kind of polynomials, the kind of information that's encoded by the Tutte polynomial. And so yes, there's going to be places where they don't overlap, but we're very clear on where they do. Okay. Same game. I'm not going to spend much time on this slide, but this does answer your question. Same game in the multivariable case. This edge here has weights A and B. I use the edge weights on the planar graph to induce the weight system on the oriented medial graph to make things line up. So exactly the same game. All right. Let me just be a little more specific about some of the information that these generalized transition polynomials pick up that the Tutte polynomial doesn't. One of the polynomials that did I say this was the same story? This is exactly the same story. The relation between the transition polynomial and the Penrose polynomial is exactly the relation between the Tutte polynomial and the chromatic polynomial. I mean, it's just that kind of thing. The Penrose polynomial is actually one of my favorite things in the whole world. I think there's not been enough work done on this. It was
The title of his paper is wonderful.
Yeah.
the paper itself. The paper itself.
Well, what does it
If there's
mean?
anyone who hasn't read this paper, the paper is worth reading just for the beauty of the diagrams. I mean, they're priceless. It's really lovely. But this Penrose polynomial is a priori, right from the beginning, computed by vertex transitions. So it's just naturally an evaluation of this transition polynomial. But one of the remarkable things about this Penrose polynomial is literally two separate evaluations of it. You have the number of 3-edge colorings of a 3-regular graph, which is equivalent to the 4-color theorem. So it's just a remarkable object. And this transition polynomial picks it up. It also picks up, I beg pardon?
What's its relation to the circular transition polynomial?
The Penrose polynomial is an evaluation of it. If you pick the right weights, you have to just pick these weights.
Oh,
And if you pick these weights, you get the Penrose polynomial. If you pick these other weights, you get the circuit partition polynomial. If you pick these other weights, you get the circuit partition polynomial in the oriented case. If you pick these, not these weights, you get the Kaufman bracket from knot theory. Okay? It's just, you just pick the right weights, and it gets polynomials that are computed by transitions at the vertices. So this was good fun. Now, it's all very well and good and lovely and exciting to create graph polynomials. You can kind of do it all day. Generating functions are very easy to create. The hard bit is getting information out of them. So it's also very lovely to create a polynomial and say, oh, look, it assimilates all of these other polynomials. But it's sort of hard to say, not to say, well, so what if you can't do anything with it? All right. So at this point, we were looking for tools, and in particular, algebraic tools for extracting information. Now I get to say that word, hop algebra. Okay. I'm not going to define a Hopf algebra, but I'll give you one of my favorite little baby examples of a Hopf algebra, and it kind of covers the essence. So you've got doesn't have to be an infinite dimensional vector space, but you have a vector space, and for the binomial bialgebra, it's just the monomials in X. This is an algebra, meaning that you have an associative map from the tensor product of the vector space back to the vector space that's associative. And here it's just polynomial multiplication. This is good. Co-algebra means you've got a co-multiplication, a co-associative co-multiplication that takes you back. Okay, so you take something in the vector space to the tensor product, and here it splits up a monomial into its pieces, and the coefficient is the binomial coefficient, which is why this is called the binomial bialgebra. Okay, you become a bialgebra if these two maps are compatible, and meaning that, for example, this co-multiplication is a multiplication map. Okay. So if you do this to a pair that are multiplied, it's the same as doing co-multiplication to each of them and then multiplying those. All right. And then you get an extra, I'm not going to spend time on the antipode, but you get an extra little map that has some nice properties mapping the vector space back to the vector space. Good? Yeah? Okay. And this answers your question about why I used the pair weights instead of what you said was natural. And I agree that what you said was natural. This is why I made a more refined structure. Okay? If gamma is the set of these graphs with weight systems, I get a finite part, it's a locally finite partially ordered set with order relation, just subgraph. So nothing deep here. Just subgraph with induced weight system. Eulerian subgraph. I gotta be a little careful here. Eulerian subgraph with induced weight system. And this thing is also closed under disjoint union, which is just, think of as the direct product in here. Those two properties mean that I get to call this set a hereditary family. And once you've got a hereditary family, you get the Hopf algebra for free because some other wonderful people did a ton of work. I love when other people do a ton of work. So this thing is an incidence Hopf algebra. And in fact, Bill Schmidt, because he did a ton of work, falls out immediately what the structure is. So I didn't have to find this. It was just kind of given. And the antipode. I beg your pardon? G, I beg your pardon, where? Multiplication, this is disjoint union. Okay, so in the hereditary family, the disjoint union or direct sum gives you the multiplication, and the partially ordered set, the breakdowns of the locally finite partially ordered set, give you the breakdowns that you need for the co-multiplication. Yeah.
So the co-multiplication is all ways of decomposing this Eulerian graph
Into two Eulerian subgraphs that cover it.
Right.
Edge disjoint Eulerian subgraphs that cover it. Mm-hmm. Exactly. And they inherit their weight system from the big one. Okay. But I got to be able to split those at its edges, so I need to know which half edges go in A1 and which half edges go in A2, so I need to know which pair weights go in which. Yeah. And what's very happy making about this is that and this was work. Okay, at some point I had to do some work. I couldn't just let other people, but the transition polynomial is a Hopf algebra map.
Sorry,
On this Hopf algebra.
Could you go over the antipode again?
The antipode takes partitions of G into ordered partitions. This is important. Ordered partitions of G into edge disjoint Eulerian subgraphs. So you can think of them as the K partitions where we don't care about what the exact circuit is, just that set of edges. Did I answer your question?
Yeah.
Sort of? I could try again.
So the P equals 2 case, I mean the cardinality of P equals 2 case is exactly what comes up in the co-multiplication.
Yes, yes. Yes. Yep. And you don't have the separator hanging in the way. Yeah. Yep.
Antipode is kind of the evaluation of the polynomial at minus x instead of x, or not?
You were right on the money.
No, the
Yeah.
polynomial. No, the
Yeah, but
polynomial
that's-
J, I mean.
Yeah. Yeah, it's got that correlation. Okay. So, right here. Yes. This is exactly what you're saying. Beautiful. You can do it next. Yes. What you get from that are these structural identities. And from the co-multiplication, you get the structural identity that lets you break down your input into two pieces and evaluate that on subgraphs. And from the antipode, it lets you go from positive to negative to get more information.
So to say that it's a Hopf algebra map is to prove these two identities?
No, to say that it's a Hopf algebra map is to show that this comes out of it. To show that it's a Hopf algebra map is to say that it's multiplicative, that it respects the co-multiplication.
Respects the co-multiplication is just your first identity?
Yeah, the other way around. Once I've shown that it respects the co-multiplication, the identity comes out immediately by just kind of turning the...
I know. But what I'm trying to do is rephrase your complete theorem without referring to Hopf algebras.
Oh, the answer is, okay, hold on. The answer is yes, you can do it. And you certainly can do it without Hopf algebras. You can prove this directly. And in fact, it was done both by Bolabosh and myself, just directly combinatorially. There's a proof for doing this directly combinatorially that's analogous to Tutte's identity for the chromatic polynomial, where you just count different colorings and you just color the Eulerian subgraphs 2 different colors, and you can play the same game. That was just sort of work. I mean, it's nice to have a combinatorial proof. This came for free because Bill Schmidt had done all the work.
Right.
So,
But
yeah, so I did it, you know, so I did it the easy way first.
Right. But in other words, there's a short list of identities which are equivalent to the abstract statement about it being a
Yes,
Hopf algebra.
yes, you can think about it that way.
Okay, good. That-
Yeah.
you're
Yeah,
sure-
I mean, in some sense, combinatorial, if you think about it, the Hopf algebra, this structure, I mean, it just gives you a placeholder, you know? It gives you a placeholder to keep track of things. It's not really, I'm not pushing the limits at all of Hopf algebra theory. So,
But the Tutte or multivariate Tutte polynomial does not have a Hopf algebra?
this would be a bit of a holy grail. Nigel Ray, somebody can help me out here, in the 80s or 90s, with one of his students, Green, thought they had something like this, and it was a little shaky. A Hopf algebra structure for the Tutte polynomial, or something that you could recover that would give us a phenomenal amount of information. We don't have it. I would love to have it. There's some, I haven't had time, there's some people here I'd kind of like to talk to about that. Okay, so I forgot where I was, but we're good. So these give you really nice, powerful theoretic tools. And I'm right on the money. Look at this. This would be the last slide. We were able to get interpretations for those circuit partition polynomials for all integers, where previously they'd only been known for 3. So now we know what they're counting. You know, you plug in 228 into the Martin polynomial, and we know what it's counting. I mean, after a while, you're sort of recounting stuff. You know, the polynomials just get big. You're just counting reorderings. But certainly, in the lower numbers, these are valuable interpretations. Because of that medial graph connection between the Tutte polynomial and the circuit partition polynomials, it meant that we were able to give combinatorial interpretations for the Tutte polynomial on the diagonal, again, for all integers, whereas previously, other than the trivial stuff like 1, 1, and 0, 0, it had only been known for -1 and 3. And this came straight out of the co-multiplication identity. And we were also able to use the antipode that let us switch the signs. We had interpretations for the Penrose polynomial for positive integers, and it let us know what the negative integers were counting. So that was really good fun. So there we go. And I'm not even making anybody wait for tea.
So what were they counting?
I'm sorry?
So what were they counting?
In the Tutte polynomial case, the planar graph, they're counting structures in the medial graph because that's what the association was. But yeah, they're counting families of Eulerian cycles and permutations of those.
So
Lasthenius is a conjecture about powers of 2 dividing the coefficients of the evaluation
Yes.
of the diagonal tuple. And then
And he gave it to me, and I failed.
you failed. Your
Thank you for bringing that up, Gordon.
Your interpretation doesn't.
It gives one small step further, but not the full. Not the full. And maybe it could be pushed farther by somebody cleverer than me. That would be not hard to find such a person. So it would be worth taking another look at, because he also gave it to me, I think about 6 months before my 2 boys came. So maybe somebody not sleep deprived. Yeah.
For the region of the Martin's polynomial where it is not that, there is any kind of equivalent of Welsh plane where you know if it is HB complete or calculable in a sense? Or can it be done?
That has not, that question has not been addressed to my knowledge. I mean, clearly because it's on planar graphs, the equivalent to the top polynomial can't be done on the diagonal. In general, this thing can't be done. The transition polynomials are hard. What the plane, the equivalent of the Tutte plane would look like, nobody's looked at that question at all.
But there can be some nice formulas even when it's number P complete.
Yes, yes. Yeah, I mean, there's,
Permanent.
this is, I mean,
Something.
like I said, this was only started in '77. Las Vegas's stuff wasn't until the '80s. So work really didn't start getting going on this into the '90s. So there's just tons and tons and tons of questions that haven't been asked. Yeah.
May I ask, so this, is there categorification of this transition?
I'm sorry, I missed your middle word.
Is there a categorification of this transition? Like there is this.
Not that I know of.
Hovanov homology.
Not that I know of, and it's no, I don't believe that's been done. Yeah. Lots of open stuff.
Yes, I just wanted to make a comment about your multivariate polynomial stuff. So,
You want to
from
go
my
back
point
to?
of view, the one with 2 variables where you have product over XE in the set A and then product over YE in a complement is more or less
This.
trivially equivalent to a
Yes.
one variable one just by pulling out an appropriate prefactor.
Yes.
So to me, what's interesting about what you've done is you have a kind of no-go theorem.
Yes.
There are a whole bunch of properties that
Oh.
you'd like to have.
Let me make one thing. Please let me interrupt you because I'm a little embarrassed all of a sudden. When you said you have a no-go theorem, let me make real clear
All
here.
these other people and you.
Zaslavsky, the heart of this, those 3 small graphs were there. Then Bolobash and Reardon did this from another perspective. The heart of this theory really is with these 3 folks. You'll notice this in very small letters, okay? It was very hard to build on these 2 papers because they're from very different perspectives. This paper here is a mild generalization of these 2 and a lot of housekeeping.
This
Okay, so I don't want you saying it's mine.
Okay. So
Okay,
all
and the
of you guys-
Bolobash and Reardon paper, from your perspective, really hits on this. That what they were looking for was really to establish that they had pushed out to no-go. That's it.
Right.
Okay, if you've got a commutative ring, that's it.
Right. So what? So
You
what
know,
I'm.
don't try to go any further.
Right. So I'll restrict myself to the
Yeah.
case where the commutative ring is a field, and avoid the degenerate cases where a lot of
Yeah.
these weights are 0. And it basically says there are a bunch of properties you'd like to have. Ideally, you'd like to have the deletion contraction relation hold in the same form for ordinary edges, for loops, and for bridges. It's better to not have to worry what kind of an edge you're working on.
But you lose, for every freedom you take,
Yeah, so
you lose something.
So you also want it to be multiplicative on disjoint unions, and you ideally like it to be multiplicative on unions at a cut vertex. And what you show is you can't have everything, except for very trivial cases where the polynomial is essentially a constant. But you can have almost everything in various ways. The way that a lot of us write the multivariate Tutte polynomial for graphs, which is basically the one you wrote on the next slide, but forget about,
Sorry.
forward, yeah.
Yeah.
Just
and
write
also-
that and make all the y's 1. That one has all of the right properties. You have the same deletion contraction relation for all 3 types of edges. You have multiplicativity on disjoint unions. The only thing you don't have is, instead of having multiplicativity over blocks, you have multiplicativity over blocks up to a factor q. That's the only difference. You have virtually all the properties you'd like. But because disjoint unions and blocks are treated differently, that can't work for matroids. So if you want to make it work for matroids, you pull out a factor of q to the number of vertices. Then it automatically works for matroids. You automatically get multiplicativity over both types of unions. But then what goes wrong is the deletion contraction relation is a little different for loops than it is for normal edges or bridges.
Yeah.
And then I guess there's a dual one where it can go bad for bridges and is okay for loops and normal edges. So you can't quite get everything.
But you
there are
pushed
these
out to a
various
point where
versions that get everything but one.
But you've pushed out to this point where you're at a little teeter-totter. Everything that you can get for a price.
Right. But the point is that all of these differ from each other by little prefactors. Q to the number of vertices, or maybe Q to the number of components, something like that. So the various prefactors you can play with to get different one of those 5 properties to fail.
Yeah, that's a nice way to summarize that. Yeah.
Has anybody tried to take the log of these polynomials? Or
Take the
logarithm, or do some transformation
No.
on trivia? We have learned that it
I-
give a lot of information.
Yeah, I can almost answer all of those questions. Has anybody tried blank? No. Yeah, please. Nobody's looked at the zeros. I mean, you've got real integer coefficients.
I mean, for the transition one.
Yeah, yeah, or even what they mean.
Well,
Yeah.
with the multivariable Tutte, a lot of people have looked at the zeros.
Yeah, no, oh, obviously, yes. The answer to, with the Tutte question, has anybody done blank, is usually yes, which is part of why I chose to talk about this here. I also want to say, in some sense, like often happens with theoretical math, this is solutions in search of a problem. So one of the things that I was sort of looking here, we're like learning that the Ising model was a summation over Eulerian graphs, the Eulerian graphs that you were talking about, these topological Tutte polynomials. I didn't go there, but this transition polynomial also has similar kinds of relations to topological Tutte polynomial and the interlace polynomial. So there's a question that if you had put in the blank, the answer would have been yes. So those kinds of questions, people were talking about looking at states of lattices where you were looking for Eulerian orientations of the lattices, those kinds of questions. So.
Okay, thanks very much.